All right, my AB kids, we are almost there. We're starting Unit 7, and this one is a lot of work with integrals. The first section, the sections we're going to do are 7.1 to 7.4, and then 7.6 to 7.8. So we're not doing 7.5, it's a BC topic. So that's how it's kind of split up this time. The first section is on modeling with differential equations, and you might ask yourself, sounds like a song, right? Dy over dx, differential equations, what is that? And that's when you have a derivative going on, a differential equation, that equals something. And it equals, could be, I'm just going to put something. That's a differential equation. We've seen them before. We did them back in section 6.8 when we had to find a specific particular, they use the word particular, solution to an equation. So we're going to be looking today at verbiage. This almost seems more like an English class sort of than a math class. You're taking the words and you're translating them into a math equation. So the words that they're going to use that are going to give us a key as to how we're going to set up equations are they're either directly proportional. Most times they just use the word proportional and they assume it's directly proportional. So if you see proportional, you're going to follow this pattern. If an A is proportional to B, then A equals some constant k times b. And if it's inversely proportional, then it's going to be reciprocal. So now your A equals k over b. But the way that I'm going to do this, and he did it, he kind of erred more towards this first way, but I kind of like doing it. When you see the word inverse, it's going to be A equals k times 1 over b. So where it's proportional, it's k times b. When it's inversely proportional, it's k times 1 over b. And so for my brain kind of follows this thinking, but you'll see it when we get to doing the problems. You can really combine them and put them into a single fraction rather than two separate pieces. All right, so write a differential equation that describes each relationship. If necessary, use k as the constant of proportionality. So the first one is the rate of change of y with respect to x. Let's just take that much. The rate of change is like a derivative, so it's going to be dy over dx. The rate of change of y with respect to x looks like this. Is proportional, k times something. Right? It's proportional, so it's k times something. What is the something? It's proportional to the product of t, and product means times, and the rate of change of w with respect to x. Rate of change, again, that's a derivative, dw over dx, and that's it. That's your answer. The rate of change of y with respect to x is proportional, k times the product of t, and the rate of change of w with respect to x. You're translating the English into a math sentence. Number 2. The force F of a spring on a trampoline can be related to the distance d it is stretched. The rate of change of the quantity of F with respect to the distance d, let's do that. The rate of change of F with respect to the distance d equals inversely proportional. Well, that's going to be k times 1 over inversely proportional to the natural logarithm of the distance d. The natural logarithm of the distance d. So there's your sentence. Now, then you get into, now they want you to take it an extra step. If the rate of change of F is 3 units per centimeter, then the spring has been stretched 0.2 centimeters. And what is the differential equation for this situation? What they just did in this pink part that I just highlighted is that's going to allow you to find k. What they want you to do, and they're not specifically telling you that, but they gave you enough information so that you can figure out what k actually is. So let's come over here and do this. The rate of change of F is 3 units per centimeter. That's this piece. So you know that that part of your equation is 3. You don't know what k is, you're trying to find it. And distance that the spring has been stretched is 0.2 centimeters. So that's going to be 1 over the ln of 0.2. And so you go to your handy dandy calculator and you calculate out what K is. It turns out that K equals about, you're rounding, negative 4.828. And so they want you to write the actual differential equation that has that specific proportionality factor. And so all you need to do is replace the K. So here's your final answer. dF over dd equals negative 4.828 times 1 over the ln of d. So if they give you that extra information, they're looking for you to find what K is, and then you're plugging that into your equation, and that's the end. All right, last example. Let's see if we can figure this one out. Mr. Bruce is swimming in a straight line across a lake. His position from starting point is given by the position formula, P of t, where t is measured in minutes since the start of the swim. During the first 30 minutes, Mr. Bruce's acceleration is proportional to the cube root of the time since he started to swim. Write a differential equation that describes this relationship. Well, the first thing is, you know, it's proportional, right? And it's an acceleration. Well, how on earth do I get acceleration from a position formula? Remember how position's a lot of times S of t? They're just calling it P of t. Doesn't really matter. It's still the same thing. So if I'm trying to get to the second derivative, then I need, it looks like this when you write it. Now we're using this. This is always the differential equation. You know how you have choices for writing derivatives. If it's y, you can write it y prime. You can write it dy over dx. You've got all those choices. You always want to keep this as a ratio. So this is the second derivative of position with respect to time. And that's the notation that you use to talk second derivatives on this in a differential equation type of thing, where you're looking to keep it as a ratio. Now that is proportional. My acceleration is proportional, K times, and then it tells you the rest of this. Acceleration, proportional, cube root of time. Well, what would that look like? The cube root of time. Write in a differential equation that describes this relationship, and you're done. That's it. They did not give you, by the way, they gave you extra information in here. You don't care. I don't care during the first 30 seconds. Doesn't matter. It's not part of what my equation is going to be. They only want you to find that differential equation. Where in this one, they gave you kind of specifics about two different pieces, and you were able to figure out what K is. You don't have enough information to go any further with this, nor did they ask you to. All right, so believe it or not, that is all of the examples. We're going to go right to a couple problems from the practice. First one I chose is number 3. By the way, there's nothing new I can tell you about these. That's it. You got the whole lesson. All right, the rate of change of r with respect to x is proportional to m and inversely proportional to the square of d. Now be careful if it says square or square root, right? Watch your wording. Rate of change of r, dr, rate with respect to x over dx is proportional to m. So first piece is an m. And inversely proportional, what do you do with inverses? Put them 1 over the square of d. That's it. That's the whole equation. Now the way that they put it, you might see it on the curriculum video if you watch that video, they put it all together as a single fraction, and they do it right from the beginning. It's the same thing. It doesn't matter. I can have it in 3 pieces. I can put it together as one. In my mind, I just like to keep it as separate. Okay, it's talking about this, then it's talking about this, then it's talking about that. And that way, for me, it makes it just a little simpler. So I keep them separate. All right, number 7 is the next one I chose. Mr. Kelly's running down his street. His position is given by the function P of t, where t is measured in seconds since the start of his run. His acceleration is proportional to the square root of the time since the start of his run. His acceleration is 0.0277 kilometers per second at 3 seconds. In other words, this time they want you, since they gave us this information with the 2 pieces, we want to be able to find what K is. So they're kind of saying that without saying that. But let's start at the beginning. His position is given by yada yada. His acceleration, We want the second derivative. So we're looking for, like we did in that last example, d squared p over dt squared is the notation that we use for acceleration, is equals proportional k times the square root of the time, since he started his run. All right, so step number 2, we want to figure out what k is. So they told me that the acceleration is 0.0277 k times at 3 seconds, the square root of 3. So I take 0.0277, I divide by the square root of 3, and lo and behold, it gives me a k that is 0.016. And so I put it together in my formula. They want to know what the differential equation would look like. D squared p over dt squared. They're not really, they're second derivatives. So I guess I probably shouldn't put it in that terms. Equals 0.016, and then the square root of t. Replace your k. And then you're done. All right, flipping one more question to do, and then we're going to call it a day on this section, and that is number 12. Number 12 I thought might confuse you a little bit. You know you love these test prep questions. The rate at which the quantity B of a certain substance decays is proportional to the amount of substance present at a given time. Which of the following is a differential equation that could describe this relationship? All right, so if I'm thinking about this one, there's a few words that they've got going on here. First of all, the quantity of B is decaying and is proportional, the rate at which the quantity B of a substance decays is proportional to the amount of the substance. That means dB over dt has to equal, is proportional, k times the amount of the substance. Well, the substance is B, right? The quantity B of a certain substance decays and is proportional to the amount of the substance. So it's proportional to the substance. Which of the following differentials could describe this relationship? Well, one of your key pieces here, first of all, you can eliminate these two, right? They don't have the times the B. And I have this word decays. What does that mean that constant has to be? Is it going to be positive or negative? And so if something is decaying, obviously it's going to be negative. You have 2 choices left. Even without much information, you can determine that that's got to be a negative constant of proportionality because your substance is getting smaller. All right, that takes care of section 7.1. It's a short and sweet one. Just watch the verbiage, and I will see you in class. Email me if you've got questions.